Okay, greetings everybody. Thanks for joining us. As Andrew mentioned, my name is Glenn Oswald. I'm with Advantage Engineering. We are an industrial heat transfer company. We were born in the plastics industry, 1977, but our history goes way back into the 50s for heat transfer equipment for the plastics industry. I've been with Advantage for a little over 30 years. So with that said, the sizing cards that you see on the screen, the two blue ones are the ones that apply to the plastics industry. Those are general conversions and also what we call a rule of thumb sizing. We touch base on injection molding, obviously extrusion, blow molding, other parts of cooling applications or heat transfer applications within the industry. On the back page, or this card is obviously got one front and back. On the back page, we do some conversions and typical pipe sizing for flow rates. The card on the right, which says glycol chiller sizing, really doesn't pertain to the plastics industry. That is for the brewing industry, which we do participate in, and a lot of these pop-up microbreweries have Advantage chilling equipment. But with that said, we're talking about plastics, so we'll forget about the brewing thing for a minute. But feel free to have a beer while you're listening to this presentation if you'd like. Okay. With that said,
I'm going to jump in real quick. I forgot to mention, if you guys have any questions during the presentation, if you go down to the bottom of your Zoom window, there should be a chat button. Just click on that and just enter any questions you have in during the presentation in there, and we'll do our best to answer them at the end.
Okay. Okay, so this presentation is basically definitions, formulas, and sizing for heat transfer. Again, my name is Glenn Oswald. I'm with Advantage Engineering. I'm a regional sales manager. So the overview of this presentation is we're going to talk about what heat transfer is and how it applies to the plastics industry. We're going to talk about terms used in the heat transfer language, if you will. The formulas that we commonly use to size your heat transfer needs. The products that are used to transfer this heat. And Andrew, real quick, I got this little green thing that says you are sharing. Can I get rid of that?
I think that's got to stay there, unfortunately.
Okay. All right. Okay, so what is heat transfer? Well, heat transfer, the technical definition is a method where two or different bodies, I should say, seek a temperature equilibrium. And the best way to describe that is to picture a glass of water with ice cubes in it. You're having a drink of water. The bodies are the glass, the water, and the ice. Three different bodies at three different temperatures. The glass is at room temperature, the water is at the temperature that it came out of the faucet, and the ice is at typically 32 degrees. Well, if you don't drink that water and ice, and you just let it sit on the table, eventually over time, you're going to see condensation around the outside of the glass. You're going to see no ice and all water. Well, those three different temperatures or bodies at different temperatures eventually over time have equalized in temperature. The glass is the same temperature, the water is the same temperature, and because the ice is a lower temperature, it has melted and it has transferred its energy to the water. So that is heat transfer. It has equalized temperature or has met the equilibrium. So if there's one thing in this presentation that you walk away with, that you remember, please remember that energy or heat is not created or destroyed. It is only transferred. You cannot create energy. You can only transfer it from one source to another. And that, and by definition, is where heat transfer comes into. The products that are manufactured to transfer the heat are based on this principle that energy is not created or destroyed. It is only transferred. In any heat transfer cycle, the final destination of that heat is the ambient air, the outside ambient air, or the plant facility air, which eventually will go outside. So regardless of what heat transfer challenge you have, the heat or energy will transfer eventually to the ambient air. Okay. As we all know, heat needs to be added. Oh, let me back up. If I say heat, I mean energy, and if I say energy, I mean heat. They're two synonymous words. You can call it energy transfer or heat transfer. Heat transfer seems to be the term that everybody uses. So anyway, heat needs to be added or removed from material being processed. That's one application. Heat needs to be removed from hydraulic pumps, recirculating pumps. Heat exchangers need to exchange heat. Barrels need to add or have heat removed from them. Air compressors, again, have to be cooled. That heat has, or the energy has to be transferred away from the compressors. Typically in the plastics industry, especially when we're processing material, that heat needs to be removed as quickly as possible. So you can get a better cycle time or further or bigger or longer throughput rates, regardless or depending on what your application is. Now, heat transfer terms. Obviously, it's a foundation to get a handle on terms that we use in the heat transfer applications, so we understand what we're dealing with. Again, heat transfer is a balancing act between your process and Mother Nature. You are transferring heat from your process as you're manufacturing your products, and that heat or energy is being transferred eventually to Mother Nature, i.e. the ambient air. One term that you probably already know is BTUs. You hear that term all the time. You're specifically probably with your air conditioner at home. How many BTUs is your air conditioner rated for? Well, BTU stands for British Thermal Unit. And basically what the definition of that is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So if you have a pound of water in a bucket and it's at a certain temperature, it takes 1 BTU to raise that pound of water 1 degree Fahrenheit. Now you'll find as we go through this that water is the basis of heat transfer. It's the center point, if you will. We compare everything to water. because water has a specific heat value, and we'll get into that term shortly, of 1. Everything else, every material, whether it's a liquid or a solid, will have a different specific heat value from 1. In other words, it'll be different than water. So that's the foundation. Water is the foundation for heat transfer when it comes to the formulas that we use. So you probably heard the word ton. Ton is the definition of how many BTUs in a refrigeration ton. So in other words, 1 ton of refrigeration equals 12,000 BTUs. If you're familiar with tower water or evaporative cooling towers, a ton is defined as 15,000 BTUs equals 1 ton. So when we're talking refrigeration, and typically when we're talking any heat transfer, and we tell you that you need 3 tons worth of cooling, that converts to about 36,000 BTUs per hour. If we're talking tower tons, we're dealing with 45,000 BTUs per hour. Turbulent flow. I know you've all heard turbulent flow. Basically, the definition of turbulent flow is the velocity at a given point where that fluid is erratically changing in magnitude and direction. In other words, as the water or fluid is traveling through a channel or a pipe, it's bouncing off the surfaces of that channel or pipe. By doing that is defined as turbulent flow and is more or the most efficient for heat transfer. There's a Reynolds number or a formula called Reynolds number, that can determine turbulent flow in a channel or a pipe. And it's basically a value times the GPM divided by the viscosity and the of that fluid and the diameter of the channel in inches. So you multiply this constant of 3160 times the GPM divided by the viscosity times the diameter of the channel. If it's greater than 5,000, then you can be assured that you have turbulent flow through that channel or that pipe. Now, this applies for direct movement through your process at the use point. In other words, if we're talking about injection molding, it's through the channels in the mold. If we're talking about a central chiller with pipes overhead delivering water to multiple points, turbulent flow is really not that important. It's at the use point that we're dealing with. With that said, the opposite of turbulent flow is laminar flow. And laminar flow is basically a slow-moving fluid that is flowing through the channel or the pipe, but it's not moving fast enough and it's not erratic enough to transfer heat. It's like a slow-moving river, if you will. And again, if we use the Reynolds number, if it's less than 2,000, then we have laminar flow and poor heat transfer. Specific heat. Okay, now this is the term that I was talking about a few minutes ago. Specific heat is a value that is assigned to materials or liquids, fluids, if you will, that quantify its ability to transfer heat or energy. So the definition is the ratio of the the quantity of heat required to raise the temperature of a body 1 degree compared to raising the temperature of an equal mass of water 1 degree. So as I was saying earlier, the specific heat value of water is 1. The specific heat value of other fluids and materials are going to be less than 1. With that said, by definition, that means materials have or cannot transfer their heat as quickly or as efficiently as water does. Latent heat is another term. You probably don't hear this very much, at least in the heat transfer discussion. But basically, it's defined as the heat given off as a material changes in temperature or fusion or vaporization, I should say, other than a change in temperature. So using the ice and the water definition or analogy, latent heat, when water turns to ice and vice versa, the temperature of that material or that water or ice does not change. It stays at 32 degrees, but it takes 72 BTUs in order for that material to change from a liquid to a solid or vice versa, even though it has not changed in temperature. You don't hear us talk about that very often because we've already taken that latent heat value, if you will, in consideration when we're trying to figure out what your heat transfer needs are. So if we tell you you need 3 tons of cooling, then we've taken into account that that latent heat has already been calculated into that material. Now we're going to talk about formulas. There are a couple of formulas that we deal with to try and hone in on your cooling needs. One formula is called material BTUs, and basically we take the materials that you're processing, the pounds per hour, multiplied that by that specific heat value of that particular material, and the delta T of that material. In other words, the temperature in and the temperature out. What we need, how many BTUs we need to pull out of that material in an hour's time. When we have that, we simply divide that by 12,000 BTUs, because remember that's what the definition of a ton is, to come up with the amount of tons of cooling that we need for your application. So in other words, pounds per hour times specific heat times delta T divided by 12,000 equals tons. The next formula is fluid BTUs. If we don't know the material pounds per hour, or if you have an application that's existing and you don't know what the cooling needs are for that, but we know what the GPM is of the fluid, we can figure out how many BTUs is required or it generates. And then we simply take the gallons per minute of the fluid times 60 minutes times the pounds per hour of that fluid, again, times that specific heat value of that fluid, times the delta T. So as an example, if somebody says, I don't know what my heat load is, but I do know that I'm flowing 30 gallons per minute of water, and my delta T is 15 degrees, we can, by this formula, we can tell you how many BTUs per hour you're generating. And then convert that to tons after we figure out what the BTUs are. Again, since ton equals 12,000 BTUs, that formula basically becomes a derivative of, whoops, I need to go back. Well, anyway, well, maybe it's a weighted water test. I can't remember. Okay, here we go. This formula, again, is the same as the fluid formula. We call it weighted water, but it's for water and not a fluid other than water. Gallons per minute times 60 minutes times 8.34 pounds per gallon of water times the specific heat of that water, which is 1, times the delta T divided by 12,000. Water weighs 8.34 pounds per gallon, 60 minutes in an hour. That formula can be condensed down to GPM times 500 divided by delta T divided by 12,000, or GPM times delta T divided by 24. And you'll hear us talk about determining what the heat load is by multiplying the GPM times the delta T of the water divided by 24. Next subject is flow. There's an old saying that if there's no flow, there's no load. Or if you know your flow, you're going to know your load. And basically what that means is efficient heat transfer cannot occur without flow. Remember turbulent flow. If we don't have turbulent flow, we have laminar flow, then we're going to have poor heat transfer. If we have turbulent flow, then odds are that our heat transfer efficiency is going to be very good. But if we have no flow, we have no load. But if we know our flow, then we can know our load. Again, Reynolds number, we achieve 5,000 or greater, you can be assured that you're going to have turbulent flow through your channels or your piping. But turbulent flow is only one aspect of the equation. The Reynolds number confirms that turbulent flow, but it does not guarantee heat transfer. Well, that's a repeat. I apologize. So now let's talk about the products that we use for heat transfer. Evaporative cooling tower systems. This is a product that basically takes advantage of Mother Nature and uses the ambient air temperature and humidity level to absorb the heat that you're transferring from your process directly to the tower system, or from a chiller, a water condensed chiller, to the tower system and eventually to Mother Nature. A tower system works on a wet bulb temperature, which is basically, again, the ambient temperature and the humidity level in the air at any given time. That said, a evaporative cooling tower works or is rated at a 78-degree wet bulb. Your wet bulb temperature is changing every hour. Depends on what the ambient temperature is. It depends on what the humidity level is. So we take a psychrometric chart at if we know what the ambient temperature is and we know what the humidity level is, we can look at that chart and we can determine what that wet bulb temperature is. The higher the wet bulb temperature, well, let me back up. At 78-degree wet bulb temperature, a 100-ton tower cell or system is capable of removing 100 tons of energy, which, remember, that is at 15,000 BTUs per hour. Using 78-degree wet bulb temperature as the benchmark, if you go below, or if the wet bulb temperature is lower than 78, the efficiency of that tower, or the capacity of that tower cell, actually grows. So a 100-ton tower at, say, 75-degree wet bulb could be as high as 110 tons worth of cooling capacity. If you go above, or if the wet bulb temperature is above 78 degrees, the capacity of that tower cell or that system is going to decrease. And at 79-degree wet bulb, 1 degree above 78, you're actually going to experience a 10% derate in the capacity or the ability of that tower to reject heat into the ambient air. The majority of the United States and in your area, 78-degree wet bulb or lower is typically achieved 98% of the time, the annual hours of a year. So you take the annual hours, 24 hours times 365 days, multiply it by 98%, or 98, yeah, 98%, excuse me. That's how many hours you're going to have 78-degree wet bulb temperature or lower. So the majority of the time, you're going to experience 78-degree wet bulb temperature. And that wet bulb temperature is important because the tower cell works on a 7-degree delta T, or approach, excuse me. Meaning at 78-degree wet bulb, you're going to get 85-degree water out of the cell if you have 95-degree water entering, in other words, a 10-degree delta T. That said, you'll have 85-degree water or less 98% of the hours in a year, which is usually, that 85-degree water is usually more than adequate for cooling hydraulics, air compressors, heat exchangers, and in some cases, your process, or supplying water to temperature controllers and other use points. Tower system consists of a tower cell, which is outdoors. The tower cell has a fan. It draws air across the wet deck. Water is falling through that wet deck, if you will, and that is where the heat exchange takes place. Typically, or another part of the tower system is a pumping station, a process pump, a tower pump, and those are typically sized for 3 gallons per minute to both the process and the tower. So that tank, that holding tank, is typically sized for 6 gallons per ton. So if you have a 100-ton tower, then we are going to most likely recommend a tank of at least 600 gallons or larger to facilitate the volume of water that you need to have in that pumping station. This is a picture of some of the towers. This one on the left, it's a single cell tower. The one on the right or in the background is 3 fans. So basically, we gang them up to facilitate larger capacity towers. Advantage offers single cells starting at 45 tons and then multiple cells going all the way up to 540 tons. This is a typical pumping station. Again, we have a tank We have a process pump, which is, you can see in the foreground, a tower pump, which is to the left, and then I typically have a standby pump that works for both, either the standby pump or the process pump, in case one of those pumps goes down for maintenance. And keep in mind, these are mechanical devices, so eventually you will have to service them in one manner or another. And then a control cabinet or control console with switches to turn the pumps on or off, and a controller that will control the thermostat to turn the tower pump on and the tower fan on to maintain your set point temperature. And keep in mind, with the tower system, 85 degrees is the typical set point temperature, but you can set it at any temperature that you want. You can set it at 70, 60 degrees if you want. But always remember that the temperature that you get out of the tower is always based on that wet bulb temperature. So in the summer, odds are you're going to get 85 degrees, between 80 and 85 degrees. In the winter, you could probably get anywhere between 50 and or above, because the wet bulb temperature makes the tower more efficient. And if the wet bulb temperature is, say, at 43 degrees, you could get 50-degree water out of there. Now, I caution you to not just decide you're going to run your tower as low as possible in the winter, because you don't want to freeze the water up out in the tower. Other products are chillers. Those are refrigeration devices that incorporate a recirculation system to flow tempered fluid through the process or to other heat transfer devices. Typical delivery temperatures for the chillers are between 20 and, it says 70 degrees here. It's actually 80 degrees now with the 410 refrigerant. 50 degrees is the design temperature. In other words, a 10-ton chiller is rated at 10 tons at 50 degrees, leaving water temperature. Anything below that, the capacity of that chiller is derated. Anything above that, you get a little bit more capacity out of that chiller. There are two types of chillers that are available. One is air condensed, and that's simply using the ambient air to transfer the heat from your process to the chiller to the ambient air. And that ambient air could be your plant air or your outdoor air. Depends on what type of device or chiller that we're or that you need. Water condensed is the other version, and again, it transfers the heat from your process to the refrigeration system to another source of water, which is typically tower water. So instead of using the ambient air to condense the refrigerant, we're using another source of water, which is tower water. And just as a comment, water condensed chillers are typically less expensive than air condensed chillers. They consume less energy because we're not driving fans or blowers, and typically they require less maintenance than air-cooled chillers. This is an example of an air-cooled chiller, packaged or portable chiller, if you will. Again, it's going to have the refrigeration system, it's going to have the pumping system, and it's going to have the control system. This is a picture of a central chiller that delivers, oh, let me back up. The portable chiller is designed typically to deliver water or a water glycol to one use point. Whether it's a mold or an extrusion trough, or a heat exchanger. It's designed to deliver water or water glycol mix to a single use point. The central chiller, like what's in this picture, is designed to deliver chilled water to multiple use points. That's why we call it a central chiller. It's centrally located, and it has a piping system that's delivering water to multiple use points. Typically, the central chiller is going to incorporate one or two or more refrigerant systems or zones. And the control system is going to stage those zones based on your cooling needs at any given time. That cooling need is determined by the leaving water temperature going out to your process, and it's sending that temperature to the controller, and the controller is determining if it's at the set point temperature or if it's above or below, and then makes adjustments with the refrigerant circuits to maintain your set point temperature. So if it's at 50 and that your set point's at 50 degrees, then odds are it's hit that point where it's doing its job, and you only need to run one circuit, and maybe that circuit needs to run at a 50% capacity. But if that temperature goes up, that means you've added more load to the process. The controller is going to say, okay, I need to turn the second zone on in order to cool that water down to maintain 50 degrees. We have a process pump delivering the water out to the process, and then we have the smaller pump that's delivering the warm water to the refrigerant circuit evaporators to do the heat transfer from the refrigeration system for the process water, or so it goes back to your process. And then again, a standby pump to work for either the process or the evaporator pump. Another transfer product is temperature controllers. Temperature controllers are designed to recirculate tempered water through a single use point. And they incorporate a recirculating pump, typically a heater, a cooling valve, and a control device. And basically, what the temperature controller is doing is it's relying on another source of cooling water, such as a chiller or tower water. With that said, it's recirculating the tempered water through the process. That tempered water is gaining heat or raising the temperature of that fluid or the water. And when it gets back to the temperature controller, the controller is telling a cooling valve to dump water and inject cold water into it in order to maintain that set point temperature, or close the valve, turn on the heater because the water temperature or the fluid temperature is too low and we need to add heat to the water by energizing the heater. Again, it's designed to recirculate tempered fluid through a process by allowing a portion of heated fluid to be discharged, which is the heat transfer, out of that loop, while at the same time injecting cold fluid into that loop to maintain the temperature. There are two types of temperature controllers. We have water temperature controllers, and we have, or let me back up, those are designed for up to 250 degrees or 300 degrees. There's what we call open loop or direct injection, or that definition is basically the temperature controller. When it opens its cooling valve, the cooling water directly injects into that loop, and discharges back to the chiller. There are closed loop temperature controllers where the recirculation loop stays or does not touch the cooling water loop. It's isolated by a heat exchanger. And the reason for that is you might need to run a glycol fluid through the process for whatever reason, or some type of treated water. But your cooling water system, whether it's a chiller or tower, you don't want those two fluids to mix. So that's where a closed loop temperature controller comes into play. And in some cases, temperature controllers can be used as booster pumps. In other words, your process is being cooled by a central chiller or a tower system, but the flow from that system is not turbulent, and then therefore you need to put a booster pump in that loop to boost the fluid flow to make it turbulent so you can transfer the heat better or more efficiently. Excuse me. There are oil temperature controllers, same concept as the water temperature controller, but instead of using water or a water glycol, we use a heat transfer fluid. They're a little bit different than water temperature controllers. They have to be self-contained, if you will. So we typically don't have, where they're not direct injection, they're typically closed loop, if you want to call that, because they incorporate, for cooling, they have to have a heat exchanger, and we have to have the cooling source in order to extract that heat or transfer it. They're designed for temperatures anywhere from 200 to 500 degrees, 550 on some brands. They're available in what we call heat only. There's no heat exchanger. So the application is a heat only or continuous heating application where no cooling is required. The application has to have heat in order for the product to cure or solidify, however you want to say it. Therefore, we don't have a heat exchanger in there because there's no cooling. If you need cooling, we have to have the heat exchanger because we can't mix oil and water, so to speak. And it's very important to make sure that heat exchanger is sized properly for the heat transfer. There are standard heat exchangers available or supplied with the typical basic standard hot oil units, but it's really important to make sure that heat exchanger is sized properly, because your flow rate or your heat input into the process might be 12 kW or a 1 horse application, but your delta T's might be higher, and that heat exchanger that is standard might not be big enough. So it's important to make sure that the heat exchanger is sized properly. Again, in water temperature controllers, especially open loop, it's not that critical because the cooling valve typically is large enough for just about every application. But in hot oil units, the heat exchanger really needs to be paid attention to. Again, here's a typical sample of standard temperature controllers. The small one typically is up to 16 kW, 3 horse. The larger one is 5 and 7.5 horse and 34 kW. Believe it or not, the hot oil units that we offer are in the bigger package. Water quality. Water quality is very important. As you're processing, or your water system is pushing water through pipes and channels and whatnot, they're picking up, or tower systems, they're picking up debris, if you will, calcium, other things. And those need to be contained or controlled. Otherwise, you're going to start plating your surfaces in your process, and you're going to get, you're going to get scale buildup. And believe it or not, 1/64th of an inch of scale on a surface that is trying to transfer heat could reduce your transfer capabilities of up to 25%. And that's pretty significant. So if you're having heat transfer issues, everything was working fine one day, and then all of a sudden the efficiency starts to drop, and you determine that the equipment is functioning properly, then odds are that you're building up scale within the recirculation system, and your heat transfer is not as efficient as it needs to be. So saying that, filtering your solids out of your water to prevent this plating is very important. And there's a lot of filters out there, different types. There's strainers, sand filters, bag filters, cartridge filters, you name it. As long as you have a filtration system in your system, you're doing yourself a favor. I personally would always recommend full flow filtration, especially on the central systems, because you're filtering 100% of the water. Other filters that are side stream, you're only filtering roughly 10% of the system. And although that's good, it's not great. And a lot of that scale can get back out into your system and plate channels and whatnot. Your water pH needs to be under control. 7 to 10 is a typical good target to control your pH so you don't get acidic water to start eating channels, the materials that your channels might be in. And you also need to control algae or organism growth. And that's typically done with chemical treatment or non-chemical treatment. With today's advances in technology and whatnot, there's a lot of non-chemical treatment products on the market. Some work, some don't, but chemical treatment is the alternative to that. And let me say that Advantage and other heat transfer equipment manufacturers are not good water quality managers, because we're in our location, you're in your location, your water is different than our water, and you really need to have a good local water quality management team test your water, assess it, and make recommendations to what needs to be done to keep your water quality top notch. Other ways of doing water quality, I guess is the best way to say it. You can run glycol. Typically, glycol is not necessary unless you're running less than 48 degrees Fahrenheit in a chiller. And I guess as a side note, let me just say, please don't put glycol in a tower system. That's not what it's designed for. Through the evaporation process in the tower, if you put glycol in the system and that water evaporates, you're just going to have a sludgy mess in your tower and in your wet decking and in your tank, and it's not going to be a good thing. So don't put glycol in your tower system. But if you use a glycol, you need to use an industrial grade inhibited propylene glycol. Do not use automotive antifreeze. Automotive antifreeze is designed for closed systems. In other words, not exposed to atmosphere, and they have silicates in them that, if exposed to the atmosphere over time, those silicates start to plate out. And again, you'll get that jelly mess that I mentioned if you were to run glycol in a tower. Glycol is designed for lower freeze points, but a lot of people will use glycol to help control water quality, corrosion, if you will. I personally don't think that's the best thing to do, specifically because glycol is a heat transfer deterrent. That said, if you run a 30% mix of glycol, the specific heat value, remember being 1 for water, is now 0.91. So you've essentially lost 90% of your, or excuse me, 10% of your heat transfer capability with that glycol. Now, what's that mean? Well, if your load is 10 tons, you're really only transferring 9 tons of energy. So you might have to get a bigger chiller in order to compensate for that loss in heat transfer capability. Some people will run 50% mix. At that point, you're down 17%. If you run a glycol and you want to use it as a corrosion preventer in water quality management, 30% is the minimum that you have to run in order for it to be effective. If you're running it because the chiller is below 48 degrees, 30% mix is designed to go down to 10 degrees Fahrenheit. So in the majority of applications that we run into or experience, running anything above 30% is really not necessary. This is a typical picture of a full flow solids filter. The water comes in through the side at the bottom, goes through a cone or a screen, if you will, traps the solids. The clean water goes out the top side and out to the process. Again, this is a full flow. This is just one example of a filter. Again, there's bag filters, cartridge filters. I think that's it. Okay. This is a typical diagram of transferring heat. With that said, there's a lot of ways that we can do this with different devices. The top one, and there's a lot more than just these 4 examples, but at the top, the heat source, where the energy's at, transfers to a temperature controller, which in turn transfers to a water-cooled chiller, which in turn transfers the energy to a tower system, which in turn transfers or dumps the energy to its final destination, which is the ambient air. The second one, again, heat source back to a temperature controller, to an air-cooled chiller, to the ambient air. Third example, heat source to a water-cooled chiller, to a tower system, to the ambient air. And then the fourth one, I guess I duplicated. Oh, no, the fourth one is the heat source to a chiller, air-cooled chiller, to the ambient air. Okay, with that said, the conclusions are: energy is not created or destroyed, it's only transferred. Fluid flow is key to efficient heat transfer. The formulas that we use for flow and load help us determine the necessary, or what your load is and what the necessary device is to achieve that heat transfer. And water quality management is important to maintain your efficient heat transfer. That's it. The next presentation that we're going to do from Advantage will be, how does a chiller work? And at this moment, I don't know when that's going to happen. Andrew can give you more details at a later date.